Thank you very much, Sophocles, for the extremely kind introduction, and thank you all very, very much for having me. It's been awesome to be able to visit for the week. And so today I'm excited to be talking to you about true and pseudo-true parameter values, which is joint work with Harvey and Jake, who are PhD students at Harvard. So the sort of motivation for what I'm going to talk about today is the sad fact that most economic models used in empirical practice seem likely to be misspecified. Right, where the sources of this misspecification can stem from many, many, many different sources. Right, for instance, sometimes we think we have incorrect assumptions about functional form or the information available to economic agents. Sometimes we think that the parameters or effects we're interested in may be heterogeneous across different agents. Or we think, we're taking something like an instrumental variables approach, but our instruments are wrong. Now, response to these concerns, prominent in literature and econometrics, has been a focus on inference methods that are valid for what are called pseudo-true parameter values. Pseudo-true parameter values are values that fit the data best in some statistical sense, where exactly what statistical sense we're using depends on the estimation method we use. For instance, if I write down a model and then I fit it by, say, running maximum likelihood, versus fitting it by matching particular data moments to particular model moments, those two strategies are going to imply different pseudo-true values in general. Now, the sort of literature on robust inference on pseudo-true values focuses on developing standard errors for uncertainty quantification, which are robust in the sense that they measure the sampling uncertainty around whatever it is that my estimator recovers. Right, so I have a confidence interval which is guaranteed to cover the pseudo-true parameter value with probability 95%, leaving open the question of whether I wanted the pseudo-true value in the first place. In particular, as has been widely discussed in the econometrics and other literatures, these pseudo-true parameter values that we're guaranteed to recover under model misspecification don't necessarily answer the economic questions that motivated our economic analysis in the first place. For instance, White 1982, which is a paper which proposed now very popular methods for misspecification robust standard errors for maximum likelihood, notes that the estimator converges to a well-defined limit and may or may not be consistent for particular parameters of interest. Much more recently, Hansen in 2021, which is thinking about misspecification robust inference for generalized method of moment type models, notes that there are a number of limitations to give economic interpretation to pseudo-true parameter values. Right, so as these papers highlight, we sort of know how to do statistical inference on pseudo-true values, but it's not so clear that they're actually something we care about in the first place. And so in what I talk about today, I want to revisit this distinction between true and pseudo-true values and think about when the pseudo-true actually gives us something we might want. In particular, an important observation motivating what I'm going to talk about today is that in lots and lots of economic contexts, the true values for quantities of interest remain well-defined, at least conceptually, even when my model is wrong, even when my parametric assumptions fail. For instance, in many economic models, we're interested in things like counterfactual outcomes or average treatment effects or optimal policies, where all of these are objects which arguably have an objective existence independent of the model. Of course, I'm using the model to try to learn what they are. But even when my model is wrong, right, the optimal policy, or sort of what would happen if we were to implement some policy, conceptually remains well-defined. And as long as these targets remain well-defined, we face a meaningful choice between trying to do inference on true and pseudo-true parameter values, where I would argue this choice presents important trade-offs. In particular, true parameter values are usually not going to be point identified once we allow the possibility that the model is wrong. Right? Once I say my model is wrong, and you ask me sort of what's the counterfactual outcome under some policy intervention you're proposing, the typical answer is I don't know. At the same time, pseudo-true parameter values will usually be point identified, we'll usually be able to recover from the data, but not necessarily answer the question we want. So to sort of think about this trade-off today, I'm going to make a couple simplifying assumptions. First, I'm going to assume the researcher fits a linear in parameters minimum distance model, where the class of models I'll be talking about includes things like ordinary least squares or linear IV or logistic regression. Second, I'm going to make a big leap and just completely abstract from sampling uncertainty. Specifically, I'm just going to treat the joint distribution of the data as observed and think about what we can achieve in such a setting. In the context of those assumptions, I'm going to consider three questions. First, what does a researcher concerned that their model may be wrong need to believe about the data generating process in order to be satisfied summarizing the data via the minimum distance objective? Or I'll make exactly what I mean by this much more precise. Second, over and above that, as a researcher to believe to be satisfied summarizing the data via a pseudo-true parameter value, as in this usual practice of focusing inference on pseudo-true values. Finally, when the first set of conditions here holds, but the second set of conditions fails, what else can we do? So in this context, I'll show first that a Bayesian is content to summarize the data using the minimum distance objective if and only if their prior beliefs regarding model misspecification satisfy a particular rotation invariance condition, where I'll of course make that condition precise later in the talk. Second, a Bayesian who further believes that the degree of model misspecification is small may be content to focus on the pseudo-true value, but only if their prior on the degree of misspecification is thin-tailed, again in a sense that I'll make precise. Finally, I'll show that we can construct misspecification robust confidence intervals for the true parameter value, not the pseudo-true, that are valid so long as the first set of conditions holds, even when the second set of conditions does not. To preview that last result a bit further, right, what we're going to show is that there exists a particular confidence interval which requires no input from the researcher beyond the weighting matrix, which is something that people are already picking to conduct estimation, is centered at the pseudo-true value, and has width proportional to the square root of a population J statistic. Right? So basically, the width of this confidence interval gets wider the more badly violated the over-identifying restrictions of my model are in my data. We show that this confidence interval covers the true parameter value with ex-ante probability, 1 minus alpha, under any prior that is compatible with the minimum distance objective in the sense of 1 on my previous slide. Right? So sort of over this class of priors we derive that are consistent with minimum distance in a formal sense, this guarantees coverage. And importantly, this result holds with no assumption on the severity of model misspecification. Right? So sort of this confidence interval remains valid even when the model is arbitrarily severely specified, provided our priors on misspecification satisfy this condition. Consequently, we think that these confidence intervals may be a natural option for summarizing misspecification-driven uncertainty in settings where we were already maybe happy with priors that have this structure. Again, I'll be much more precise about all of this later in the lecture. So with that, let me start making this all more precise and dive in a bit more to this distinction between true and pseudo-true parameter values. So the setting I'll have in mind here is one where we get to observe a distribution P on a set script D. You could think of this as abstracting a setting where I observe an infinitely large sample of observations drawn from the distribution P, where if I observe an infinitely large sample, I can estimate the distribution to arbitrary precision. So today I'm just going to say I observed the distribution in the first place. We're going to be interested in some parameters. For the sake of today's talk, I'll assume it's scalar valued. And we're going to have a model which implies a set of moments which are functions of the parameter theta and the data distribution P. In particular, our model is going to imply I of P minus x of P times theta is equal to 0, where y are known functions, and I'll assume that x of P is non-zero. If this thing has a solution, the solution is unique. Now, we're going to be concerned that this model may be misspecified, in the sense that if I think about the true data distribution quantity of interest pair, the true P theta pair, and I evaluate my moment conditions at that true pair, they're in fact not equal to 0, but instead take some non-zero value eta. To make the discussion in today's talk more concrete, I'm going to use the linear IV model as a running example. So in particular, suppose observed data D consists of an outcome U, a 0, 1 treatment variable T, and a k-dimensional vector of instruments C. where I'll generally be assuming that k is bigger than 1. So I have more instruments than I have endogenous variables. We're going to be interested in learning the average treatment effect of t on u. And to do that, we write down the usual linear instrumental variables model, where we're going to say that the outcome u is equal to the treatment times a parameter theta plus epsilon, where we'll assume that epsilon is orthogonal to the instruments. Right? You could covariance equivalently assume linearly residualized. Now, this model is going to imply linear. Y here is just going to be the expectation of the instruments times the outcome, which is a transformation of the reduced form regression coefficient. And X is going to be the expectation of the instruments times the endogenous regressor, which is just a transformation of the first stage. Now, as I said, right, here we want to think about settings where the model may be misspecified. So to think formally about misspecification in this setting, let me write down sort of a potential outcome model that's going to nest the linear model I just started with. Specifically, suppose I have potential outcomes u indexed by t and z. Right? So this is describing for each individual I what outcome they would have if assigned a particular treatment variable little t and a particular instrument vector little z. Similarly, suppose I have potential treatments ti indexed by z. The observed treatments then correspond to the potential treatments associated with the realized instruments, and the observed outcomes correspond to the realized treatments and the realized instruments. Now, in this setting, I said we're interested in learning the average treatment effect, which in the context of this potential outcomes model is just this object. Right? So this is just the average over the population of the outcome difference when I switch the treatment 0 to 1. Right? So on average over the population, if I assign everyone to treatment versus I assign no one to treatment, how does the outcome differ? Now, if I take this potential outcomes model and I impose 3 restrictions. First, exclusion, which says that the potential outcomes don't directly depend on the instrument z. Right? So the potential outcomes are unchanged z prime for every unit. Are homogeneous. So if I look at that difference has variance 0 across units, right? So the treatment effect is the same for everybody. And finally, that the instruments are exogenous in the sense that they're orthogonal to the untreated potential outcomes. You can show that this potential outcomes model reduces to the linear IV model I wrote down before, right? So under these 3 assumptions, recover the usual IV model, and the average treatment effect theta is going to solve my IV moment condition. Sadly, in most applications, lots and lots of contexts where there are things we would like to use as an instrument, but the instrument, at least arguably, has a direct effect on the outcome. Moreover, in many contexts, we think treatment effects are heterogeneous. Right? There are lots of treatments out there in the world where the effect the treatment has for you could be different than the effect the treatment has for me. Finally, there are also lots of things we would like. Exogeneity starts to seem kind of doubtful. And when any of these conditions fails, the average treatment effect theta will typically fail to solve the internal variable's moment condition. So if I evaluate the IV moment condition at the ATE, I'm going to get some non-zero vector eta. Right, for concreteness today, I'm going to focus my discussion on a case where I maintain 1 and 3, but I relax 2. If I relax 2, I say treatment effects may be heterogeneous. Further impose Imbens and Angrist 94 style. Effect. Right, an average treatment effect for the types of people induced to change their behavior by that instrument. But, right, a well-established result in the literature, going back to that paper, is that the local average, the average treatment in general. Right, the average treatment effect for people who respond to a particular instrument may be different than the average over everybody. In particular, if I let this symbol denote the element-wise quotient, and I of the vector y over the vector x. The vector parameter of one instrument at a time, instrumental variable. Right, so these are basically the IV coefficients that I estimate by running using just the first instrument by itself, then the second instrument by itself, then the third instrument by itself, and so on. Consequently, if I let this little circle denote the element-wise product, in this IV example, you can show that eta, right, that is the value of the IV moment conditions evaluated at the true parameter value, is equal to beta, right, the vector of one at a time IV estimands, minus the average treatment effect theta, vector. Now, in the usual IV model, any instrument that I use, I'm still going to recover the same quantity, right? Local average treatment effects are local average treatment effects are average treatment effects, so beta equals theta. This first term is 0, and eta equals 0. Under the Imbens and Ingres model, it's going to be non-zero when the local average treatment effect differs from the average treatment effect. Now, when eta equals 0, we know that theta solves the moment conditions, right? Sets the moment conditions equal 0. And therefore, theta also zeroes out the minimum distance objective, which is just equal to moment conditions prime times the positive definite weighting matrix W. More generally, even when my moment conditions fail to hold, right, I can define a pseudo-true parameter value as the parameter which minimizes this objective function in population, which in the simple linear model I'm working with here just looks like this, right? Which basically just looks like weighting by W. Right, again, to make this concrete, think of the linear IV model. If you run linear IV with this particular weighting matrix, then the pseudo-true parameter value corresponds to two states least squares. Now, as I said, when eta equals 0, when the model is correctly specified, the pseudo-true parameter value is the truth, and my minimum distance objective evaluated the pseudo-true parameter value is 0. Right, so I recover the true parameter value, and I get to zero out my objective function. Life is good. When eta is not 0, what's wrong necessarily needs to hold. And in particular, the true and pseudo-true parameter values may be very different, raising a question when, if ever, we should be interested in this pseudo-true object. Right, again, looping back to the motivation at the beginning, misspecification robust standard errors give us valid confidence intervals for this pseudo-true thing, but that leaves entirely open the question of when this pseudo-true thing is something we would actually want. So to start that question, note that the pseudo-true parameter value is determined by the minimum distance objective function. So therefore, if I'm going to be happy summarizing the data using the pseudo-true value, I must also be happy summarizing it via the minimum distance objective, right? Because the pseudo-true parameter value is just a coarsening of the objective function. Right, and so let's start by thinking about when we would be happy summarizing the data via the minimum distance objective. To answer that, let's think about a Bayesian decision maker who just comes into the world with a prior pi over the parameter of interest theta and the data distribution p, where the model is misspecified. Right, so under my prior, I think the probability that the moment conditions are 0 when evaluated to the true theta p pair is less than 1. Right, so this is a prior. I'm allowing the possibility a priori that the model is wrong. In this context, I'm going to say that this decision maker is happy to summarize the data via the if and only if their posterior on theta, given the data distribution, is proportional to some function of the minimum distance objective evaluated at theta, where this function can also depend on w, x, and theta. Right, in principle, you might sort of adopt a stricter definition of summarizing via the minimum distance objective, where I say it should just be proportional to a function of the minimum distance objective theta. This weaker definition is going to be sufficient for the purposes I'm going to use it for today, so I'll work with this one. So to concisely state some conditions here, let's let pi subscript theta prior on the quantity of interest, conditional on the weighting matrix and the x's. Pi eta given theta denote the conditional prior on this misspecification vector theta given W and X. Now, I'm going to interpret pi eta given as basically a conditional prior on the model specification, motivated by the fact that under the prior pi, if I think about what's my prior distribution for the moment conditions, evaluate the true parameter value theta, conditional on that corresponds exactly to this conditional prior pi eta. Right, so pi eta basically describes conditional on this other stuff, what do I think the mean of my moment conditions is when I evaluate them at the true parameter value. So again, to make this more concrete, let's go back to linear IV. In linear IV, conditional at a time local average treatment effects, conditional on the average treatment effect theta. For instance, if our conditional prior for the local average treatment effects is normal and centered at the average treatment effect, right? So sort of I think on average, the local average treatment effects are equal to the ATE, but there's some dispersion. That corresponds to this conditional prior pi eta given theta being normal and centered at 0. So with that notational setup, we're now equipped to state the first result, which is that under some mild conditions, the posterior for theta given p depends in the sense that I said we wanted, if and only if our conditional prior on eta given theta takes this particular form. Right? So basically the prior density for eta given theta is equal to some potentially theta dependent function f evaluated at eta prime w eta, where f here is a non-negative integrable function. So I think it's helpful to unpack that result a bit. So in particular, the condition that our conditional prior on eta given theta takes this form holds if and only if our conditional prior deemed forms of misspecification that yield the same value for my minimum distance objective function evaluated the true parameter value equally likely. Right, so basically if two different forms of misspecification imply that when I evaluate the minimum distance objective at the ATE, I get a value of 5. Under my prior, those two things have to be equally likely. Right, is basically what this is saying. This in turn is going to be true if and only if the direction of root w times eta is uniformly distributed under my prior. Put another way, root w times eta divided by its length has to be uniformly distributed on the unit sphere under my prior. Right? That's the only way that I find all things that produce the same value of this equally likely. Now, this one's an obvious to us. I think this makes a lot of sense. In particular, suppose that weren't the case. Informative about the direction of root w times eta. Well, in that case, if I have an informative prior on that object, I should be using that information to estimate the parameter theta. But the minimum distance objective throws this information away. Right? If I think about two forms of two data generating processes P that imply the same length for root w times eta, they necessarily also imply the same minimum distance objective. Right? Because the length of root w eta is just the square root of this thing. Right, so if it's going to be a good idea for me to do minimum distance, it must be that I don't have information on this direction. If I had information on this direction, I should be using it. So next, let's turn to sort of go beyond this and ask, right, note that focusing on pseudo-true parameter values is a step beyond just focusing on the minimum distance objective. Right? Because I'm basically going from saying I want to use this objective function to I just want to use the argument of the objective. Right? Of course, I should note, in practice, we would usually report the pseudo-true parameter value along with a standard error, but those standard errors go to 0 in large samples. Exactly 0 in the population setting I'm thinking about here, so I'm not going to worry about those. So the question I now want to ask is when, if ever, are we going to be happy summarizing the data using the pseudo-true parameter value? So it would certainly suffice that the posterior is more or less a point mass at the pseudo-true value. Right? Because if I know my posterior distribution is a point mass at the pseudo-true value, and you tell me where the pseudo-true value is, you told me everything I need to know about my posterior. Right, but in fact, we argue in the paper the posterior collapsing to a point mass is actually going to be more or less necessary and sufficient under some additional conditions. So let's think about when that happens. When does the posterior collapse to a point mass at the pseudo-true value? In particular, I'm going to provide some conditions on my joint prior on the true parameter value in the data generating process such that my posterior on the data generating process after seeing the data converges to a point mass at the pseudo-true value in the limit c goes to 0. And for simplicity in stating this condition, I'm going to assume the conditional prior on eta given theta doesn't depend on theta, which is just saying that my priors on the true value for the parameter of interest and the degree of model misspecification as measured by eta are independent. All right, so we show that in this case, if I consider priors pi eta given c that are of the same u eta, but now I normalize by 1 over c, the resulting posterior distributions are going to converge to the pseudo-true value as c goes to 0, and if I take the function f and I evaluate it at a times u and divide it by its value evaluated at u, where a is greater than 1, again, I think it's helpful to sort of unpack what that result is saying. So first, note that the prior variance of eta, right, the variance of this misspecification vector under are proportional to c. Right, so in this proposition where I think about the limit to 0, that's thinking about the limit as basically my prior says, at least a priori, the degree of misspecification is arbitrarily small. Right, so these are priors that think the model is misspecified, but think the deviation from the model is very, very, very small, at least in the limit. The other condition I needed for the result was this sort of funny-looking condition on the function f, right? That basically the limit as I take the point u where I'm evaluating it to infinity goes to 0. So what this requires is that the misspecification prior pi eta has thin tails. And specifically that the function fu goes to 0 at a fast polynomial rate as I take the u value where I'm evaluating it off to infinity. If my prior on misspecification corresponds to a normal, but fails when my prior on misspecification corresponds to a t. So again, it wasn't obvious to us ex ante that the thickness of the tail of the prior would matter here, so let me try to give a little intuition for why it does. Intuitively, right, the thickness of the tail for my prior on misspecification matters because it determines how I react once I see my model is wrong. In particular, suppose that my over-identifying restrictions are violated in the sense that the minimum of my population objective function, which I'll denote by J of W, think of this as a population J, suppose that's really positive. Well, by definition, right, we know that if I take my objective function, I evaluated the true parameter value theta, that gives me eta prime W eta, which must be greater than or equal to the minimized value. Right, so basically, if I see that the population J statistic is strictly positive, that tells me that eta is non-zero and my model is wrong. Now, if I think about thin-tailed priors, and I consider this c goes to 0 limit, right, so thin-tailed priors where I also think a priori the degree of misspecification is very small, you can show that what's going to happen is my posterior is going to think that there is probably not much more misspecification than indicated by the J statistic. And specifically, my posterior will think that eta prime W eta is only slightly larger than the J statistic, which means, right, that basically the objective of value at the true parameter value is only slightly larger than the minimized value, but the minimized value occurs at the pseudo-true, so that's going to imply that the true must be approximately the pseudo-true. By contrast, if I think about thick-tailed priors, even as c goes to 0, I'm going to continue to think it's possible that the is much worse than what's indicated by my J statistic. With the consequence that I also think it's possible that the true parameter value differs substantially from the pseudo-true. Again, to make this concrete, let's go back to the linear IV example. And suppose my prior on the average treatment effect is flat, just to make life easy. Specification vector eta is normal. Then you can show that my posterior on the average treatment effect, given this centered value, for instance, 2-stage least squares, with variance proportional to C. Right? So basically, as I take my prior on the degree of misspecification to 0, my posterior just converges to, my posterior distribution is a normal and collapses to 2-stage least squares. By contrast, if I take my misspecification prior to be a T distribution, you can show that as C goes to 0, the posterior on the average treatment effect is going to again centered at the 2-stage least squares estimate. But now, the posterior variance isn't going to go to 0 as the prior variance does. And in fact, the posterior variance in this case is going to converge to something that's proportional to the J statistic. Right? So this basically says that in this T case, right, larger differences between the local average treatment effects, which is essentially what the J statistic measures in this context. It's basically a version of how dispersed are the local average treatment effects that I'm getting from the different estimates. If I see that that dispersion is large, I end up with more uncertainty about the average treatment effect, even in the limit as a priori I thought the degree of misspecification is small. Right? So basically we get this very different behavior from between the normal and T cases, even though heuristically we sort of think that a normal and a T with many degrees of freedom look pretty similar. So far what I've shown is that there exist prior sequences such that the posterior converges to the pseudo-true value as I take the degree of misspecification to be small a priori. Right? Where those results also needed that the prior be thin-tailed. Right? At least from our perspective, neither of these is especially appealing. Right? There are lots of economic contexts where, at least if you ask me, the degree of misspecification probably isn't all that small. And if you ask me to specify the exact thickness of my prior on the degree of misspecification, I'm going to have a hard time. So motivated by that, we now want to think about, okay, if we aren't just going to focus on the pseudo-true value, what else can we do? So a cheap but not especially helpful answer is to note that if I'm willing to just fully specify my priors on my priors pi theta and pi eta given theta, I can always just use Bayes' rule to compute my posterior on the parameter of interest given p. Right? However, right, the posterior that I get out of this will depend on the details of the prior. Right? And we just saw with this normal in T example, relatively subtle tail features that at least I would have a hard time specifying can end up mattering quite a bit for the form of the posterior. So, again, right, if you're able to sort of do the full subjectivist Bayesian thing, life is great, but it's hard. So as an alternative, it would be nice to have some options that are justified for larger classes of priors. And I already argued that when we're doing minimum distance estimation, right, that is sort of well motivated if and only if we have our prior on eta takes this particular form. Right, our prior on eta given theta is equal to theta dependent function out, evaluated at eta w eta. Right, since we showed that our has to be of this form for the minimum distance objective to be a good data summary. Now, as I said, right, the prior takes if and only if the direction of root w times eta is uniformly distributed. Right, so what this class of priors gives us, if we're willing to use it, is a restriction on the direction of misspecification. Right, what's important to note, it leaves the magnitude of misspecification unrestricted. Eta could be, the length of eta could be big or small, but I'm restricting its direction in this sense. Now, before I sort of talk about why that's going to be useful, I want to argue just briefly that we do sometimes seem to behave as if we have informative priors on the direction of eta. In particular, it's very common or to weight moments in a way that is suboptimal under the model, right, to sort of weight our moments in a way other than the optimal weighting matrix. And one possible reason for this is to give a view about the likely directions of misspecification. And indeed, some papers in the literature actually make this pretty explicit. For example, Ben Habib et al. 2019 note that the weighting matrix W in their setting is a diagonal matrix with identical weights for all but the last moment of the wealth distribution and the mobility moments, which are overweighted 10 times, according to the prior that matching the tail of the distribution is a fundamental objective of our exercise. Right? So this says that in their setting, they think that their quantity of interest, theta, is more related to some of their moments than it is to others, which I think we can reasonably interpret as a statement about their prior on eta. Right? Basically, how do they think the mapping between their model and the actual parameter of interest works for these different moments. So far I've argued we sometimes seem to behave as if we have a prior on the direction. Now let me give some intuition for why that prior is useful. In particular, going back to the linear IB model, right? Remember that the misspecification vector eta is equal to the vector of one at a time instrumental variable estimates times the average treatment effect scaled by the first stage. Now, if I know nothing at all about the direction of eta, one possibility is that I could have eta proportional to the first stage vector. Right? That's going to happen when all of the local average treatment effects are but average treatment effect. And there's a sense in which this is a very bad scenario, right? Because in this scenario, all my instruments estimate the same quantity, but that quantity is not what I want. So my identifying restrictions hold. I can't detect that my model is wrong, but my estimate is still invalid. Now, if I put a restriction on the direction of eta, and in particular, if I assume that root W times the distribution of invariant, that bounds how often the direction of eta can be close to the direction of the first stage. Right? And in particular, it says they can be exactly equal with probability 0. Prior on the direction of misspecification limits how often I can have this scenario of sort of an invalid estimate and undetectable misspecification. So that's sort of an intuition for why this information is useful. To talk more formally about how I'm actually going to use it, recall that eta is just equal to y minus eta, where I can just pre-multiply both sides by root w and rearrange to get that root w times y is equal to root w times x plus theta plus root w eta, where, again, I've assumed the distribution of root w eta is rotation invariant. But if I define y tilde, x tilde, and eta tilde as just versions of those variables that absorb this premultiplication by root w, I can rewrite this model as y tilde equals x tilde theta plus eta tilde, where tilde is a rotation invariant error term. And moreover, you can show that the pseudo-true parameter value just corresponds to the regression coefficient of y tilde on x tilde. Right, so when I rewrite the model in this way, I see that the problem has basically reduced to I want inference on a regression coefficient theta. The pseudo-true parameter value is the regression estimate, and I've assumed the error term eta is rotation invariant. But sort of standard results that you learn in first-year statistics on t-statistic inference for the finite sample normal model actually don't rely on the error on regression errors being normal. They just rely on regression errors being rotation invariant. So if I just compute the t-statistic in this setting, which turns out to be this object, right? So it is pseudo-true parameter value minus true parameter value divided by the square root of j statistic over the number of over-identifying restrictions times this x tilde prime term. This whole thing is going to follow a standard t k minus 1 distribution, where k here is just the dimension of the moments, so k minus 1 is the number of over-identifying restrictions. Consequently, if I let tk minus 1 comma gamma just be a t critical value, if I form a confidence interval as my pseudo-true parameter value plus you can show that this interval covers the true parameter value theta with probability 1 minus alpha over all priors in the family we consider, right? Where the non-standard, right? I'm working in population here. There is no sampling uncertainty. But what I'm doing is I'm taking the indicator for the event and I'm integrating that over the prior, right? And the statement is that for all these all of the priors, probability is 1 minus alpha, thanks to sort of T-statistic algebra. Terms in this interval, I think they're pretty easily interpretable. Of course, we're centering things at the pseudo-true parameter value. We're ending up with an interval that depends on the number of over-identifying restrictions. Right? It also depends on the square root of the J statistic. So when I see that my moments are violated in sample, when I see that my over-identifying restrictions don't hold, I end up with more uncertainty about the true parameter value theta than when my over-identifying restrictions are approximately satisfied. Finally, the sigma term here corresponds to the square root of the inverse Hessian of the population objective function, which is a pretty standard sort of thing to see showing up in an asymptotic variance formula. So even though the setting here is actually quite different, the structure is similar to what we have in many other cases. Right, so the upshot of this is that if I have a prior on the direction of misspecification, I can actually use that to conduct inference on the true parameter value theta without taking any stand on whether on sort of how severe the degree of model misspecification is allowed to be. Right, and in fact, the resulting confidence intervals are trivial to implement and just correspond to T-statistics. Right, moreover, before getting to that, I argued that existing research practices suggest that, at least in some contexts, we seem to have informative priors on what forms of misspecification we think are more or less likely. Right, and so this result says that if we take those beliefs seriously, they potentially open a path to misspecification robust inference. Now, before I close, I want to note there are sort of a couple important issues I've just punted on. First, for these results, I focused on the case where the data distribution P is observed, and so just totally ignored sampling uncertainty. Second, I focused on where the moments are linear in the parameters theta. Now, at least at a high level, it seems possible to relax both of these. In particular, if the degree of misspecification were on the same order as sampling uncertainty, then basically we're going to have that both misspecification and sampling uncertainty affect the distribution of our estimators. But in this case, and so basically in this case, you could sort of repeat the analysis account for both of those terms, right? A misspecification term and a sampling uncertainty term. Moreover, under this case, there are sort of standard arguments that are going to let us rate the moments, so the restriction to linear moments may also not be too bad, right? But not doing that today, so leaving that for future work. So to summarize, today we derived a class of priors such that the minimum distance objective is a reasonable data summary. We showed that within that class, there exist sequences of thin-tailed priors such that the posterior concentrates around the pseudo-true value. We also argued that such prior sequences seem pretty unsatisfactory, and noted that even the broader class of priors we start with already restricts the direction of misspecification, and that such restrictions on the direction suffice to allow simple and actually potentially informative inference. So, thank you all very much.